Welcome, everyone, and thank you for joining us. My name is Bjorn, and I'm the host with Jinwen Wang tonight. So we are talking about produced water, which is one of the hardest streams in the industry to treat. High salinity, as you already know, variable oil content, aggressive chemistry, and these kind of conditions that rarely stay stable for long. And conventional membranes materials were not designed for that, and that's what we want to talk about. They foul, they degrade under the cleaning regimes, need to recover them, and recovery falls off well before the design case stays it should. And today we look at what changes when the membrane material itself, it tolerates oil and withstand chemical cleaning. I'm joined by Jinwen Wang. He's the VP of Products at PolyCera, and over the next minutes, Jinwen will walk through where conventional membrane hit their limits, why oil tolerances and chemical resistance matter in real operation, and what that means for design stable, high recovery treatment, offshore and onshore treatment. And if you have any questions, we are a small group. Click the button to raise your hand, and we will answer right away. So, having that said, Jinwen Wang, over to you.
Yeah. Thank you, Bjorn. First, I want to make sure my screen sharing is correct. So you can see right now, see the title size correct, or it's not, Bjorn. So you can confirm that. Okay, great. So thank you for everyone who joined today and also who is watching for the recording after today. And I'm Jinwen. I'm currently serving as the VP of Product at PolyCera Membranes. And today I would like to share our experience on using advanced membrane technology, PolyCera membrane technology for produced water treatment. So in today's webinar, I want to first just give a very brief overview of oil and gas produced water, what is produced water, how to treat it, and what's the regulation around the world. And then I will touch base on produced water treatment technologies. First, I will discuss a little bit on the conventional treatment technology and what they are good at and what they are not good at, what the drawback of the conventional technologies. Then I will talk about the membrane technology and how membrane technology being used in produced water treatment and what the advantage and disadvantage of current state-of-the-art membrane technologies. And after that, I will introduce the PolyCera organic metal membranes and talking about the feature and benefit and how those features and benefits make PolyCera an ideal candidate for oil and gas produced water treatment. Then I will introduce a few case studies, cover both our onshore and offshore experience on produced water treatment. And in the end, just welcome the questions. So let's start talking about produced water. So produced water was just water generated along with oil and gas production. So for people not in our industry, when they talk about oil and gas, they're more talking about oil and natural gas. They don't talk about water. But actually, for every barrel of crude being produced, there are often across the industry, across the world, 3 to 4 barrels of produced water is being produced along with oil. So actually, there will be, you can see there's more water produced in oil and gas industry than actually oil. So for produced water, it's usually coming from mainly 3 sources. One is the formation water, which is natural water already in the reservoir. It's coming out along with with oil, sorry. And also another big part is the fallback water, which is mainly using for hydraulic fracking. So people inject water into the reservoir to help getting oil out of ground to the surface. And those water come out with the oil and contribute to the produced water. And the other major source is reinject water, which is mainly is for the water reinjected for the pressure maintenance, and it's later produced back along with oil and gas. So with all those water coming out of along with oil and gas, is adding treatment challenges because those water are regulated in most of the world. So that will add technically and economically challenge for treat those produced water. So then I want to kind of discuss what is the composition of produced water like the main is water, of course, and along with the water, there has a lot of salt. Like usually, the TDS can be range from 10,000 milligram per liter to as high as even more than like 300,000 milligram per liter. So in some part, people call produced water salt water. Usually the pH is like between like 4 to 9, and it's of course it has oil and grease in that, and the oil can be free oil, emulsified oil, and dissolved oil. And it also can have a suspended solids range from like 10 to even higher than 500 milligram per liter solids, and have dissolved organics. Usually for the natural gas production, especially for offshore, there is actually more dissolved organics than like non-dissolved organics, and usually it's like a small molecular like a B-types. It also have heavy metals, and nowadays there's a lot of people trying to get those heavy metals, recover those heavy metals from like produced water. Not only heavy metal, also like for example lithium, like those considered as a resource coming from extract those resources from produced water. Some of the produced water has radioactive materials, making it even harder for the treatment. And of course, it will have some production chemicals. For example, fracking, people adding fracking chemicals, and it will coming out along with the produced water. And all those dissolved and non-dissolved organics will contribute to BOD and COD for produced water. So how to treat or how to use produced? We know right now there's 3 to 4 more water produced as like oil. So with that large amount of water, how we do with it? So nowadays there's just mainly 3 mainly way to treat or use produced water. Number 1 is for reinjection, which is account for probably globally, probably 15 to 25% of the water being treated that way, just water reinject pumped back to the ground, either for pressure support to enhance recovery. And the majority of the water actually around the world actually being disposed, and mainly being disposed to regulated disposal wells or pond and other permitted route to dispose the water to the regulated place. And this account for about 70 to 80%. And nowadays, people are more talking about is reuse, because that's a lot of water being produced, and we know water is a resource, and we should conserve like water. But nowadays, it's still only about 5% produced water being reused, either for like beneficial reuse for hydraulic fracking, for irrigation, for industrial cooling, for other processed water. And we believe the reuse percentage will be more and more around the globe. So there's a lot of water there, so it's a very large it's business and industry built around produced water treatment. So the data we can find is in 2024, the global produced water treatment spend is over $9 billion US. So it's about like $0.3 to $10 a barrel, about $2 to $6 per cubic meter, and it's set to double by 2034. And also nowadays, people starting to realize the produced water disposal or reinjection may cause like a problem, may cause an earthquake, especially in the US, in Texas and New Mexico. So that will add more cost to produced water treatment. So mainly add about like US $2 to $8 per barrel. So those all present a challenge, and there are a lot of like a cost associated to produce treatment, which means the more reliable and the more economical solution is needed for our industry. So I want to talk about very briefly about the regulation. So around the world, good news is around the world, the produced water is regulated, and it's more so in Europe and North America, and more strict, strong environmental control and government oversight being applied. And mainly the water is being used for like a underground injection, and not too much for surface discharge. And right now is the people more focusing on increase the percentage of reuse, but still grow very slowly. And also in Asia, there's just a standards are different in different countries, and also most of the water is being treated by reinjection. Similar like a situation in other part of the world, like South America, Africa, Australia, and Oceania, so those regions. And it's also country specific. There's not like a universal or more global standards or regional standards. And so it's mainly is a treatment, well, it's for reinjection and disposal, not too many for reuse. So now to talk about like produced water treatment technologies. Conventionally, people are using more like it depends on the oil content and the suspended solids content in produced water. And engineers usually select with the oil and the solid concentration is high. So the tanks will centrifuge will be used for separate solid and oil from water. So when the concentration of solid and oil getting lower, there will be more like a skim tank, API, CPI separator, and to be used. And when the oil concentration become much lower, then right now, most of the places are using flotation, like dissolved air flotation or hydrocycle. It's kind of the go-to technology to treat those water to meet either discharge or reinjection standards. So if the requirement become much higher, meaning you have to reduce the oil or solids to a much, much lower level, conventionally, it's just using media filters, for example, like a one shell filter or other media filters to control the solid and oil content to a much lower level. So the majority of the treatment other than the media filtration is based on the gravity or like a G-force. And so as high as a G-force be applied, then the more recovery, more removal of the oil you can achieve. However, with those mainly applied to free oil or dispersed oil, which has a much larger like a particle size, like over like 10 micron. When we're talking about like emulsified oil or even dissolved oil, the conventional method using like gravity or G-force or enhanced gravity G-force not work very well for those type of like water to remove like emulsified oil or dissolved oil. So as talked earlier, so for the like a conventional like API like a separator or gravity-based coalescer, they are very good for like free oil, like more than 100 to 150 micron. They are actually pretty effective, but they really take a fairly large footprint. So for onshore operation, it's probably okay, but for offshore, which is space limited, those usually will not be considered for those applications. And also for the smaller like concentration of oil, so use hydrocyclone or dissolved air flotation. And those are also pretty, it worked pretty well for majority of the case for reinjection or disposal. They work pretty well for those applications, those use cases. But usually people find is if you want to get the oil below 30 milligram per liter, and those technology normally cannot consistently produce the effluent treated water to meet those standards, especially when the feed concentration increase, and usually your like a treated water concentration will increase accordingly and will not meet those requirements if your requirement is high. Of course, you can use a media filter to further remove those emulsified dissolved oil, but normally the falling of media filter happen very rapidly, especially when you have very high solids and very high emulsions. Those hasn't been removed by the like a process like ahead of the media filter. So you have to either backwash a media filter or even replace media filter quite frequently, and that will increase the operational cost. So for conventional technologies, usually the process is first using tanks to remove free oil and suspended solids, then using like a flotation hydrocyclone to remove macro emulsions and colloidal solids, and then using media filter to remove micro emulsions and to meet a design goal or treatment goal. However, the issue for conventional technology is if you have a fluctuation in effluent, it will translate to the effluent, which means if you have higher concentration coming in, in the effluent, your effluent, normally you will see a spike, the increase in the effluent, which will cause the treatment, not meet the treatment process design object. Then we'll kind of go over membrane technologies, membrane separation, and usually we categorize membrane separation by the separation, what the species used to separation for microfiltration, ultrafiltration, nanofiltration, reverse osmosis. So for produced water treatment, usually microfiltration and ultrafiltration can be ideal candidate to remove suspended solids, remove free oil, and remove emulsified oil. And the nanofiltration and reverse osmosis can be remove dissolved oil or even dissolved like a salt for a certain requirement of the treatment. So membrane material have been used for and a lot of membrane materials have been used for produced water treatment. And normally is we categorize inorganic materials, for example, like a ceramic is inorganic material, and also organic material, just common organic, for example, like PVDF or polysulfone and polyester sulfone. And recently, there's some companies and they are trying to use organic inorganic hybrid material for this type of application and show some advantage over traditional inorganic and organic material, but still. Nowadays, the most common use is still the traditional ceramic inorganic and the traditional polymeric organic material membranes. So regarding configurations for produced water treatment and fresh sheet membranes, spiral wound elements, hollow fiber membranes, tubular and monolith membranes, they all being used in produced water treatment and for different treatment process and different treatment objectives. And for operation, they can be operated either inside out operation mode or outside in, depends on the feed water quality and treatment goal, also design recovery. So with membrane technology being used in produced water treatment, now people starting to using membrane to replace conventional flotation and either replace them or just using them to further polishing conventional flotation technology or conventional media filter technology using microfiltration, ultrafiltration, or using for example ion exchange membrane, or using nanofiltration or reverse osmosis membranes for further even much lower oil, much lower solids treatment to achieve more higher goals, usually for reuse. So with membrane-based technology, it can act as an absolute barrier, which means if you have a fluctuation in effluent, most of the time, not all the time, most of the time, you will find the effluent treated by membrane stay the same, can meet the your design target or meet your treatment goal. We will give examples later. So we find that it's not all the membrane can act as an absolute barrier, but most membrane can. Of course, membrane is not perfect in treating produced water, especially we're talking about there's oil, there's a solid in the produced water. It presents a challenge for membranes, cause falling, especially what we found is if you have organics and have a silica or those species, it can breach those solids and oil and form kind of like a mud, falling on the membrane surface, which is very hard to clean, and it will cause a performance decline. Sometimes those falling and performance decline is irreversible, and you cannot even clean that. And the only option is replace the membrane, which is at a lot of cost. So the challenge is how we can get a membrane to be more reliable and also more economical. So as we know, most of the polymeric membrane are not robust enough to treat trying to produce water. And following cause the forming of the membrane will cause a decrease treatment capacity, increase cleaning frequency, and shorten the membrane life. Overall, it will increase the operational cost. Of course, right now there's a lot of application are using ceramic membrane in the produced water treatment and show very promising result. Especially they are more robust compared to conventional polymeric membranes, and it's can withstanding high falling and can be cleaned relatively more easily, and also have a much longer membrane life compared to traditional polymeric membranes. But now it's still one of the issues is they usually have a fairly high price, so introduce which will incur high capital costs. Although the cost is much lower compared to 10 years ago when I was first using ceramic membrane for produced water treatment, but still compared with polymeric membranes, it's still very high cost. So then the natural question is to treat produced water, a membrane with a polymeric economics and ceramic performance is needed. So now I want to introduce what we are working at PolyCera is using organic metal materials to make advanced membrane technology product for produced water treatment. So first I want to introduce the membrane material we are using at PolyCera is called organic metal, which is they are organic polymers, and they have a very special chemical and physical structure and properties. So they can have some metallic quality and characteristics. That's why it's called organic metal. So first, it's organic, but it can have some metal properties. So we're using this material to make membranes can have stronger structure and more uniform dense like porosity on the surface and the high durabilities. And this is organic metal actually has won the Nobel Prize chemistry, and this is the first time to directly apply a Nobel Prize winning chemistry to water treatment. So with this, thanks to the benefit of the organic metal materials, and the membrane made from this material can have thermal and chemical compatibility and very excellent mechanical strength. And more importantly, it's intrinsic hydrophilic and oleophobic. I will talk about those features in details later. So with those features, the benefit we can get with using organic metal PolyCera membrane is it can have high oil tolerance. So during our test, we can find it can tolerate up to 3% oil and gas. Oil and grease in produced water, and those can be recovered by chemical cleaning. And it can run as a high flux compared to conventional polymeric membranes when treating oily produced water. Because we have a narrow pulsar distribution on the surface, so we can maintain high rejection of oil and solids. So when you have a fluctuation in the feed in the influent, and the treated water quality remains the same. And because it's organic metal material, it can handle high temperature up to 90 degrees Celsius for certain produced water, especially for certain like offshore situations. The water can be as high as like 80, 85 degrees C, and with a PolyCera membrane, it can be used directly without to cooling down the water. It also has a high acid-base stability. So for some like acid fallback water, it has a really low pH. So you can treat those water directly with a PolyCera organic membrane without adjust pH. And also we can use a very strong base to clean the membrane once it gets fouled by the oil, and without worry about the membrane get damaged by like a strong caustic cleaning. So for foaming mitigation and the membrane, I talked about earlier, the membrane has to be hydrophilic and oil tolerance. So here's the example showing the conventional polymeric materials like PVDF and polysulfone. This is picture showing we put an oil droplet on the membrane surface in water, surrounded by water. So you can see because the conventional material PVDF also they are hydrophobic and oleophilic, so the oil tend to be more spread onto the membrane surface, and which make it more sticky to the surface and harder to clean. So here's the example showing like a ceramic material and as well as the PolyCera organic metal material. We do the same thing. We put the oil droplet on the surface, surrounded by water. Because both ceramic and PolyCera, they are intrinsically hydrophilic and oleophobic. So oil doesn't want to spread, doesn't want to stick to the surface. So they form a droplet, like almost a perfect drop in the water. So it's fairly easily to clean, not stick to the surface, fairly easily to clean. So that's why we can using PolyCera materials to treat water tolerant, as I mentioned earlier, can up to 3% of the oil. So for that, you can reduce pretreatment requirement and reduce pretreatment cost. So even the membrane get fogged by the oil, so you can be more effectively clean after chemical cleaning. You can get a more effective cleaning and a higher flux recovery and for the compared with the conventional membranes. Another big feature is the membrane is backwashable. So if you, backwash can help remove the falling of the suspended solids and oil on the surface to prevent it from keep accumulating on the surface to make it harder to clean. So with the backwash, we can like lower the falling rate and increase the production production capacity and reduce the cleaning frequency and extend the membrane life. Also, I mentioned earlier for PolyCera organic metal materials, it can handle like a higher, more broad pH range and higher temperature compared to conventional materials, which is more close to ceramic membranes. And for extreme operation conditions and also extreme cleaning conditions, you can use PolyCera organic membranes and don't worry about the membrane being damaged by those conditions. Meanwhile, PolyCera membrane can withstand pure organic solvent. I mentioned earlier there's some dissolved organics in produced water, especially for offshore natural gas platform. There are a lot of like B tags in the water. So for conventional material, some long-term exposure to those dissolved organics will cause swelling, even cause membrane to lose the separation performance. But because the PolyCera membrane itself can withstand even pure organic solvent, so we can be used to treat those water with those dissolved organics without worry about the performance being sacrificed. Another big feature for PolyCera material membrane product is the membrane. The product configuration is in standard conventional spiral wound form factor, which is the benefit is very easy to design and has a fairly high like packing density to lower the footprint of the system. But also conventional spiral wound element is known to be not handle suspended solids because normally they are using like a diamond mesh spacer as a feed spacer. And if you have high solids and those diamond mesh spacer will cause clogging in the feed channel, then cause like falling, cause a performance decline for conventional spiral wound elements. So at PolyCera, for our product, we are using open model-less type of design using like those corrugated spacer, so we can create an open channel. So in the feed channel, by doing this, we can handle fairly high suspended solids in the feed water and without worry about channel clogging. So this will help reduce the pretreatment requirement on suspended solids and reduce the pretreatment cost and like both capital and operational cost for pretreatment. So overall, if we compare PolyCera membrane with a conventional tubular membrane and a conventional ceramic membrane, and we put both the CapEx and the OpEx into the configuration, also the membrane lifetime. So here we're assuming a 10 years cost of ownership, and here we are assuming PolyCera membrane will be replaced once, which means the membrane life is 5 years, and we are giving the benefit of a 10-year membrane life to tubular and ceramic. Even with that benefit, and the overall cost of ownership is 30% lower than the next best alternatives with PolyCera membranes for produced water treatment. So in summary, for current state of the membrane treatment technology for produced water, you can use polymeric, you can use ceramic, but polymeric you are enjoy the benefit of a lower cost, but you have to dealing with lower performance and higher operational cost. And you can use ceramic membrane, you can enjoy the high performance, more robust high performance, but you have to invest more, especially in capital cost for the ceramic membranes, as well as for some case, if you have to run very high recirculation rate, then you have to invest in operational costs for the energy spending on maintain the high recirculation flow. So PolyCera membranes falls very well into the spectrum, offer both polymeric-like economics, which is cheaper than like a ceramic membranes, and also the performance will be more likely more like close to ceramic membranes for produced water treatment. So for the PolyCera membrane produced treatment, we can offer is a modular design. So it's a pretreatment phase is optional, especially if the feed solids or oil is not very high, so we can eliminate this step. But if the treatment, if the feed solids and the oil is higher, and also you want a much higher recovery, so we would sometimes we will recommend using a pretreatment module, and then using the main PolyCera UF module to take care to remove all the suspended solids and the oil. And for some case, you do need a polishing, especially for dissolved oil removal, you need a polishing. So you can use either resin or using like a nanofiltration or reverse osmosis. It's also optional for polishing step. So those all can be modular design and also can be deployed to both onshore and offshore like a treatment like the sites. So now I want to talk about some case studies for onshore and offshore. First, I want to talk about our offshore produced water treatment, which we recently finished the commissioning and for CNOOC, China National Offshore Oil Companies. So we started pilot with them in February 2021, and after like almost 6 years, and we got our first full-scale project commissioned earlier this year. So here's some pictures showing the actual installation and on the platform in one of the CNOOC platform in East China Sea. So we have a contract with a CNOOC for like 9 natural gas platforms. So we commissioned one. So the total capacity is about 25,000 barrels per day, which is translated to 4,002 meters per day. And we commissioned one already, and the plan is to commission 2 more by end of this year. So the whole treatment process is we are adding PolyCera system to existing coalescer separation on the platform, and to further treat the effluent from existing coalescing system, and with the PolyCera Titan UF membranes, and also to remove all the suspended solids and all the free oil, dispersed oil, and emulsified oil. And we had a regenerable resin absorption unit after the PolyCera membrane to mainly take care of the dissolved organics, mainly BTEX, dissolved organics. And after the resin, the water will be discharged to the ocean and meet the local discharge regulation limit. So we have, for the first commissioned units, we have meet all the KPIs, all the KPIs for the project. So we are treating the treatment, the final effluent water is oil is below 12 milligram per liter, which is much lower than the national standards, which is 30 milligram per liter. And we can recover more than 90% of the water from the system, so only generate less than 10% of the waste. And we are taking on average like over 100 milligram per liter oil to the system, and they are fluctuating like between like 70, almost 70 milligram per liter to 200 milligram per liter. On average, 100 milligram per liter, and we are taking those into the system, and we are right now we are achieving 100% of the milestones. There's zero safety incident, and it meets all the certification. And it's our first attempt on this platform. So here shows some of the oil content, the feed water. You can see there's a fluctuation on the feed water, but on the treated water, we are 100% of the time the treated water is meeting the discharge standards. So here's another example for offshore produced water treatment, also for ocean discharge. This one was commissioned in 2022, and the capacity is about 6,300 barrels per day, and it's about 1,000 cubic meters per day. So this water, we are taking produced water with a fairly high temperature, 70 degrees Celsius, and the oil can be as high as 500 milligram per liter, and the solids also can be as high as 500 milligram per liter. And the treated water, we are dropping the oil down to 5 milligram per liter and drop the solid down to 1 milligram per liter, which meet the discharge requirement for the region. So the process is we are just taking the produced water without any pretreatment, just a buffer tank, and then directly fed into the PolyCera UF system. So the filtrate will go for the discharge, but the concentrate will be using settling air flotation to further minimize the concentrate volume. So the beauty here is since the concentrate is only 10 to 15% of the total produced water, so you can use a much smaller settling tank, a much smaller air flotation system on the platform to reduce the footprint of those process and also achieve a better separation efficiency with those process because you are dealing with a higher concentration. So the sludge will be further just stored in the tank and be transported out of the platform for further disposal and treatment. And also, although here we can see, although the feed oil and feed suspended solids fluctuate, and the final treated filtered oil and filtered suspended solids maintain very stable level, like oil less than 5 and TSI less than 1 milligram per liter. So here I want to share a case study we have done for onshore produced water treatment. This is a facility was commissioned in 2017 in California, which is treating tracked in produced water and from multiple oil production sites, and the treated water is for beneficial reuse. So the whole process is centered by the PolyCera membranes, and there's some chemical pretreatment, and also there's some further post-treatment mainly by reverse osmosis, because out of this water is being used for agriculture reuse. So the feed water is coming from different sites, so they are varies from site to site or batch to batch. But usually we get is the oil is also up to 500 milligram per liter, and the solids up to 500 milligram per liter. Turbidity is up to 300 NTU. And the TDS is about a brackish to brown size is about 10,000 to 20,000 milligram per liter. So here's the process in the factory. So we do coming in, we do have a tank as a primary oil water a separator. It's just a gravity-based oil water tank to separate mainly free oil and very large particles from those water. And then we go into a softening process. The softening here is mainly because there's a lot of silica in the produced water and have to be treated before going to the RO membrane, because if you have a lot of silica, then the RO membrane cannot handle. We'll have a lot of scaling issue for that. So there is a chemical softening. Mainly goal is to remove silica. So softening and flocculation, and then we'll go to the PolyCera ultrafiltration membrane trains to remove free oil, emulsified oil, and all the solids generated from the softening and flocculation process. And after the PolyCera treated, the water will go through the graduate active carbon. The goal is to remove dissolved organics and then go into two-pass reverse osmosis. So the final water is is being used for like agriculture reuse. So for the whole process, we can achieve up to like 80% recovery. And it's actually 2x cheaper than deep well injection in the region, in this region. And all treated water is being reused by local industry. Majority is used for agriculture reuse. So here we also did a study, just compare with the same process, same water, and we compare the PolyCera membrane with a reputable ceramic membrane, a ceramic membrane coming from a reputable supplier. And from our study, we can find with PolyCera membrane, we can achieve like a 11% higher water recovery, and we require 70% lower energy demand, mainly because we do not require very high recirculation compared to conventional tubular type of ceramic membranes. And also the backwash frequency is much lower, and the backwash flux is also lower with the PolyCera membranes. So we are saving 63% backwash water than ceramic membranes. And because the membrane itself is cheaper, so we're saving 58% capex, and we are saving 70% lower OPEX because we can operate at a high recovery and less energy like demand. Another thing I want to point out is with the fluctuation in the feed, we can see the ceramic PolyCera membrane filtrate is much more stable, which is the green line here, is much more stable than the ceramic filtrate, which is the orange line here, when we have a spike, when we have fluctuate in the feed water. So PolyCera membrane can have a better quality, more stable, better quality than the ceramic membrane being tested here. Another case study I want to briefly introduce here is for hydraulic fracking with water reuse. And this one has a capacity is about 7,600 barrel per day. It's about 1,200 cubic meter per day. And with also fairly high spent solids, 500 milligram per liter, fairly high oil, 100 milligram per liter. And the TDS is around 53,000 milligram per liter. So because this water will be reused to mix fracking chemicals. So before PolyCera treatment, there is some softening to reduce the hardness, so it can be meet the requirement for mixing chemicals. And with the PolyCera Titan UF membranes, we can achieve over 80% recovery for the entire UF system. And we'll reduce the solids to less than 1 milligram per liter, reduce the oil down to less than 5 milligram per liter, which is good enough for chemical mixing and for the hydraulic fracking process. And this project commissioned in 2024. Another case study is also for hydraulic fracking with water. This is for reinjection. So it's a smaller capacity, but commissioned earlier. Similar thing, we are just use PolyCera UF membrane. We can remove oil from up to 300 milligram per liter to less than 5 milligram per liter. Remove solids up to 250 milligram per liter down to less than 1 milligram per liter, which meets the requirement for fracking reinjection. And the whole process is there's no pre-treatment, just a back filter prior to PolyCera UF, and which only serve for just remove like large debris. We can also deploy containerized PolyCera system for like produced water treatment. Here is an example, also treating hydraulic fracking with water, but it's containerized system, which treating like 760 barrel per day and about 120 cubic meter per day. It's a small containerized system, can be mobile, deployed to remote site to treat those water for either reuse or reinjection. And similar, the process is we don't require pretreatment of the water, just a back filter and then using PolyCera Titan UF, and it can meet the like a hydraulic fracking either reinjection or reuse standard. So here's one example we have done with this remote system with a 30-day of operation without a chemical cleaning. So in summary, with organic metal country PolyCera membranes, it can offer high hydrophilicity or phobicity of the membrane surface, which will prevent oil forming by produced water, and it has higher permeability and high robustness. It also can have excellent thermal and chemical stability, which means it can treat high temperature water without a bar but cooling down the water. And also it can withstand a lower pH. It's ideal for acid fallback. Also, it can be cleaned by harsh chemicals. For example, you can clean with a very strong like a caustic solution at higher temperature to increase the cleaning efficiency and increase fast recovery. And it's also tolerant like falling and improve cleanability with the thermal and chemical stabilities. And it can offer significant capex and OpEx reduction compared to the next best alternative for the like membrane technology for produced water treatment. And the product is delivered in cross-flow backwashable modules. It's well suited and approved in produced water treatment. So thank you for your attention to this webinar, and now welcome questions.
Yeah, thank you very much, Jinwen Wang, for this explanation. So everybody now does have the opportunity to ask the question, to put the question in the Q&As, and we are going to answer them one by one if there are any. Jinwen Wang, in the meantime, can you maybe describe a bit? I mean, obviously you are a membrane company, but you are obviously delivering more. So what is this more, what you can bring to the table in terms of if it comes to a new produced water treatment project?
So for us, yes, thank you, Brian. This is a great question. So I think in the presentation, I didn't touch too much of what we can offer from PolyCera. So yes, we are a membrane company. We are manufacturing and supply membrane products, but also we have a complete we can offer a complete package from early evaluation of the project to pilot and also to full scale system fabrication delivery, and also to commissioning support and also after sales service. So we have a dedicated team to provide the whole supply of the process and system, and we can offer like one-stop service with for the membrane solution. For here we talk about produced water, but also for other application with membrane can be used.
Thanks a lot, Jinwen Wang. Another question that came in from Kenneth, who asked or wrote, thank you, first of all, for your great presentation, impressive references. Can you share experience regarding typical membrane lifetime of your membranes and produced water applications?
Yes, so for us, right now, the oldest installation we have done is back installed in 2021. So right now it's 2026. So it's still up and running. So we haven't replaced the membrane for this project. So it's already proven lifetime for more than 5 years. So we normally, when we design our process for the produced water treatment, so of course, it depends on feed water quality, but usually 3 to 5 years will be the lifetime expectation we will give to our customer. So 3 to 5 years.
Perfect. Thanks a lot, Jinwen Wang. There's another question from Anand. I will give him the mic and he can ask the question directly. So Anand, you can ask your question directly.
Hi, Jin. Myself, Anand from India. While most of your solutions are revolving around crude oil treatment, and I see I had been in touch with you to find out the opportunities available in the refineries. In India, I see a lot of refineries face the problem on the pretreatment prior to the RO or the ZLD. How PolyCera can pitch in over there and find some good applications over there?
Yeah, thank you for attending, and thank you for your question. So yes, for refinery, here today's topic is produced water. Yes, we have experience in refinery wastewater treatment and for reuse. And right now, most of the refinery wastewater we learned, they are most of using dissolved air flotation and biological treatment, and then prior to like our treatment for reuse or for ZLD or for reuse. So we have been used in refinery for replace dissolved air flotation to remove suspended solid and remove oil as a pre-treatment for our process. So yes, PolyCera membrane can be used and has been used in oil and gas refinery with oil and wastewater treatment. And if you have a further question or you have a project, we can definitely connect after this and discuss further.
Perfect. I haven't seen any other question yet. So if you do have, if you come up with a question afterwards or maybe tomorrow, whenever, feel free to reach out to Jinwen Wang directly, either via email or on LinkedIn. We are going to share this presentation with you guys tomorrow via email, and even then you can send an email to us if you do have any further question or if there's anything left on the table. So thank you very much for joining the webinar about produced water. Thank you very much, Jinwen Wang, for giving the presentation, and I hope everybody will have a nice evening, nice morning, wherever you are. Take care and goodbye.
Yeah, thank you so much.